and Deshidalek to all the class 12 students. Today I will be starting the next chapter of the unit calculus, that is application of derivative. Okay, so this is the second chapter of the unit calculus, and in the previous chapter we had seen derivatives. Okay, that is how can we differentiate certain functions. Okay, now in this chapter we are going to see what are the applications of the derivative of a function. Okay, in different ways we can apply derivatives. Okay, so there are a few fields where you can use derivatives, where we can apply derivatives. Okay, so the first application of derivative. Okay, so the chapter we are going to discuss today is application of derivatives. Okay, so you can apply derivatives in few topics, right? So today we are going to see how we can apply the derivative, okay, in finding the rate of change of quantities. Okay, so here in the first place we are going to see how we can apply derivative in finding the rate of change of quantities. Now when I say this rate of change of quantities, these quantities, okay, I'm going to consider the concept of mensuration, right? Like we are finding the rate of change of area, we are going to find the rate of change of surface area, volume, right? So all these things. Okay, so we are going to see how we can apply derivatives in finding the rate of change of quantities. We are taking all the mensuration quantities like area, volume, surface area. Okay, so finding all these quantities and seeing its rate of change, because if I take a circle and its area, right, then we know that the area of the circle is depending on the radius, right? If you increase the radius of the circle, area of the circle will increase. If you decrease the radius of the circle, the area will decrease, right? So area is depending on radius, right? So generally we take our function as y in terms of x. Now here we will be like y, in case of area we'll take y as the area because it is the depending variable, and radius as the independent variable in example of area of a circle. Okay, like that we will try to make a function and we will see the rate of change of that quantity with respect to the independent variable, right? So we can apply derivative in finding the rate of change of quantities. Quantities means all the mensuration quantities we are going to consider here. Okay, so there is nothing new concept in this. Okay, so I will take few examples and show you how derivatives can be applied to find the rate of change of quantities. Okay, so we will take few examples. Example 1, okay, if I give you this question, okay, find the rate of change of the area of a circle with respect to its radius. Okay, now this is the question. Find the rate of change of the area of a circle, okay, with respect to its radius. Now we know that here you are given a circle. So for every circle you can find out the area, and we know that area of the circle is depending on radius of the circle, right? So now I'm going to use that concept. Now here we are not going to take a variable in terms of y and x. You can do that also, but now you can use the first letter of the quantity as your variable. Okay, whatever you want, you can take x and y also, but first you will introduce the variables. Okay, you will write let a be the area of the circle and r be the radius. So you have a circle, okay, whose radius is r, right? And you denote a as the area of the circle. So you can use any variable here. You can write let y be the area of the circle, whatever you want. So whichever variable you want, you can take that. Okay, Now you can try to express this as okay, so we have area is equals to, what is the formula to find the area of the circle? So in this particular topic, okay, you should know all the formulas of mensuration which you had learned in class 10. Okay, so we are going to apply all those formulas here, plus you need to apply derivative on that. Okay, but without having all the formulas of the mensuration of class 10, you won't be able to do this exercise. Okay, so let me write A is equals to pi r square. We know that area of the circle is pi r square, right? Now area, okay, like we take y, here it is A, right? And like we take x, it is here r, right? So r is the independent variable and A is the dependent variable, because we know that area of the circle is depending on the radius, right? So area is expressed in terms of radius. Okay, now rate of change, okay, what is the definition, how you had defined derivative? So it is the rate of change of derivative. When you write this dy by dx, how do you say? Derivative rate of change of y with respect to x, right? Which means when you make some changes on x, what will be the rate of change on y? So that is denoted by dy by dx. Okay, so here a is depending on r, so therefore I will write dA by dr, because r is here my independent variable and I'm differentiating a with respect to r, or I'm finding the rate of change of area with respect to radius. So you should be clear with the concept of this notation, right? When you write dy by dx, it means you're finding the rate of change of y with respect to x. So whatever your variable you take on the numerator, it is independent variable, and the variable on the denominator is independent variable. Okay, so here you will write dA by dr is equals to 2, okay, pi is constant, right? Pi is constant, rate of change of r square is 2r, so therefore I can write 2 pi r. Can I do that, right? So now dA by dr is rate of change of area with respect to r, with respect to radius. Okay, so if you increase radius by 1 centimeter, then the rate of change of area with respect to r is, you have to put r is equals to 1, so that is 2 pi. Okay, like that. So this is the rate of change of area with respect to r, that is 2 pi r. Okay, so if your question is only this much, then this is your solution. It's quite simple. Okay, and if I say further, if I add area of a circle with its with respect to its radius, when okay, r is, say if I give you this 5 centimeter, if I add this more, okay, so you have to find the rate of change of the area of a circle with respect to its radius when radius is 5 centimeter. Okay, so after finding this, then you have to do it like this. So the rate of change of area with respect to its radius when r is equals to 5, so this is equals to 2 pi into 5, so that is equals to 10 pi, okay, 10 pi centimeter square per centimeter, right? So if the unit is centimeter, right? So therefore it is 10 pi centimeter square. Area, its rate of change of area. So if area is increasing, right, so then it will increase in square unit, right? So therefore area is increasing at the rate of 10 pi centimeter per square per centimeter. Okay, when radius is increased by 1 centimeter, then that will be the change in area, right? So that is 10 pi centimeter square per centimeter. So this is how you're going to write. Okay, so this is first simple example we had taken. Now I'm going to take one more example. Okay, okay, so this is the second example we are going to consider. Okay, the volume of a cube is increasing at a rate of 9 centimeter cube per second. How fast is the surface area increasing when the length of an edge is 10 centimeter? Okay, now first you read the question carefully. So here two quantities are considered, okay, of a cube. Two quantities of a cube is considered here, that is volume and surface area. Okay, now you should know what is the volume of a cube, what is the surface area of a cube, right? Okay, so first let me introduce the variables. Okay, so I will write let x be the edge of the cube, A be the surface area and V be the volume of the cube, right? Okay, so we have, now you should know what is the formula to find the volume of a cube whose side is x, what is the surface area of a cube whose side is x. So you should know both of this. So we have volume is equals to x cube and surface area, I've written here A, is equals to 6x square. So you should know these two formulas first of all. Okay, so that's why I told you you should know all the mensurations formula you had learned in class 10. Okay, so all these formulas are to be used in this particular topic, right? Okay, so now look at the question. Look at the question. What you are given is, you are given the rate of change of volume. Okay, so now we know that volume and surface area, both of them, they depend on the side of the cube, edge of the cube. Okay, so if the side of the cube is increased, then volume and surface area both will increase. If you decrease the edge or the side of the cube, then there will be a corresponding decrease in the volume and surface area. So that's quite obvious. Okay, now here we are given that the volume of cube is increasing at a rate of 9 centimeter cube per second, which means per second means we are given that the volume of the cube is changing with respect to time. So first of all, that you should know. Okay, so you are given the rate of change of volume with respect to time. You are not given the rate of change of volume with respect to side. Okay, so it means volume is depending on side, okay, and side is depending on time. So therefore we have volume is depending on time. So when there is when per second, in per second, side is being increased, corresponding to that volume is increasing. So therefore we are given the rate of change of volume with respect to time. We are not given the rate of change of volume with respect to side. So you should understand this. Okay, okay, similarly, now if side is, okay, if edge of the cube or the side of the cube, okay, is changing with respect to time, then volume and surface area will also change with respect to time, because they both depend on x, but x is depending on time. So therefore volume and surface area are both of them are depending on time. Okay, so now we are given this dv by dt is given. Okay, so that is the rate of change of volume with respect to time is given. So this is 9 centimeter cube per second. So you are given this. So dv by dt means rate of change of volume with respect to time is 9 cubic centimeter. Okay, so per second the volume of the cube is increased by 9 cubic centimeter. So this is what actually it is. Okay, now we have to find out how fast is the surface area increasing, right? With when the length of an edge is this. So now you have to find out, if you are given the rate of change of volume with respect to time, then you have to find the rate of change of surface area with respect to time. Okay, so now we are going to do that, but before this we have, okay, volume is equals to x cube, right? So we have this. So in general, what do we have? We have dv by dt. Now I'm going to use here chain rule. So volume is depending on time. Okay, so first of all, volume will depend on side, and then side is depending on time, and hence we get this volume dv by dt. So that's what I'm going to do it here. So to get the rate of change of volume with respect to time, first volume will depend on side, so that is dv by dx into, right, then this side is depending on time. So this is what chain rule is. So we are going to apply it over here. So derivative of that is the rate of change of volume with respect to time is equals to rate of change of volume with respect to side into rate of change of side with respect to time. Okay, so dv by dt is dv by dx into dx by dt. So we are using here chain rule. Okay, so this is equals to, now actually what I wanted to find out here is what is the rate of change of side with respect to time. Okay, so that I can apply this in finding the rate of change of surface area with respect to time. Okay, so dv by dt is given as 9. So this is equals to dv by dx is 3x square. dv by dx means you have to differentiate this quantity with respect to time, with respect to x, sorry. So that is 3x square into dx by dt. Okay, now here my aim is to find out dx by dt. So from this I have dx by dt, okay, this is equals to 9 upon 3x square. Okay, so that is 3 upon x square, right? Now what is dx by dt? It is 3 upon x square, which means the rate of change of side with respect to time is 3 upon x square. Okay, now what we have to find out, what is the actual question, that is how fast is the surface area increasing, right? So which means how fast means per time, with respect to time. So with respect to time, how fast is the surface area is changing. Okay, so that is we have to now find out dA by dt. So that is the rate of change of area, surface area with respect to time. So same, so it is dA by dx because surface area, okay, so it's quite same. So first of all, surface area is depending on side is depending on time, and hence surface area is depending on time. So therefore, to get the rate of change of surface area with respect to time, so this will be equals to rate of change of surface area with respect to side into dx by dt. Okay, so we are using here chain rule again. So dA by dt, that is the rate of change of surface area with respect to time is, so you have to first find out this dA by dx. Okay, so this is dA, so dA by dx is 12x, right? 6 into derivative of x squared is 2x, so that is 12x into, what is dx by dt? Here we had found using this, okay, so this is 3 upon x square. Is that clear, right? So dx by dt. So we are going, we had applied the given rate of change of volume with respect to time to find the rate of change of side with respect to time, which is 3 upon x square. Okay, now you can cancel out these two. So we have dA by dt is equals to, what is it? 12 3s are 36 divided by x, right? Okay, so this is the rate of change of surface area with respect to time, right? Now we have to find out how fast is the surface area increasing when the length of an edge or when the length of a side is 10 centimeter. So side is x, so you need to substitute the value of x, or the side is equals to 10. So now we are going to do that. So that is dA by dt, that is the rate of change of area with respect to time when x is equals to 10 is 36 upon 10, so which is 3.6, right? So you will write 3.6 centimeters square per second, right? So it is with respect to time, so therefore it is, we had written here per second. It is area, so therefore we had used squared unit. Okay, so that's 3.6 centimeters square per second. Is that clear? So this is how you are going to apply derivative, okay, in finding the rate of change of quantities. Quantities, we are taking all the mensuration quantities here, right? So this is how you're going to do. So you can see in the first example, okay, we had taken only finding the rate of change of area with respect to radius, okay, but here in this example we had taken the rate of change with respect to time. So you need to apply here chain rule, otherwise all the concepts are same, but this is more this first one is more general. Okay, we are just taking 2 variables, right? But here we are considering 3 variables. So this is how you're going to do, right? Okay, now I'll take one more example. Okay, now this is the third example which I'm going to take. Okay, it's slightly different from the previous 2 examples. Okay, so first we will read the question carefully. A ladder 5 meters long is leaning against a wall. The bottom of the ladder pulled along the ground away from the wall at the rate of 2 centimeters per second. How fast is its height on the wall decreasing when the foot of the ladder is 4 meters away from the wall? Okay, so okay, now we are going to do this. So first you try to write a rough diagram for this question. Okay, so you have this, let this be the wall and the ground. Okay, so always we will consider the wall perpendicular to the ground. Okay, and a ladder is leaned against a wall, so it will be somewhat like this. So this is your ladder, okay, so which forms a right angle triangle, okay. And now the height, this is the height of the wall, and this is the let it be base, okay, of the right triangle, and this is the ladder which we are given that height of this ladder is 5 meter long, okay. Okay, the bottom of the ladder, so this is the bottom of the ladder is pulled along the ground, okay, so it is being pulled, this is pulled, okay, so either it can be pulled this way or it can be pulled this way, so that can be done in 2 ways, but we are given that the bottom of the ladder is pulled along the ground away from the wall, which means we have to pull the ladder in this direction, okay, so it is being pulled, okay, so which means when you pull the ladder here, okay, so what happens, so when you, so this the bottom of the ladder is being pulled this way, so it will be somewhat like this, okay, it will be like this, so which means you can see as you pull the ladder in this direction, the height will decrease, height of the the right angle triangle will decrease, okay. So you have to find out how fast is its height on the wall decreasing, okay, when the foot of the ladder is 4 meter away from the wall. So when you had taken this foot of the ladder 4 meter away from the wall, okay, so then what is the rate of change, or what is how fast is the height of the wall is decreasing? So we are going to find out this, okay. So now look here, you are given the ladder is being pulled away from the ground at the rate of 2 centimeter per second. So you can first introduce the variables here. Let h be the height of the wall and b be the distance between the wall and the bottom of the ladder, okay. So we have this dB by dt, okay, so that is rate of change of this distance, okay, it is being pulled at with respect to time is, it is given as 2 centimeter per second, right, we are given this, okay. Okay, now first you will try to form a function over here, because if you have area, we know that area is depending on time and so on, right. But first we are going to look this by using Pythagoras triplet, we are going to establish a relationship between the 3 sides of this right angle triangle, okay. So we have h square plus b square is equals to, okay, this is height square plus base square is equals to 25 using Pythagoras theorem, okay. Hypotenuse square is equals to perpendicular square upon base square. So here this h is for height of the wall, okay, so don't get confused with hypotenuse, okay. So this is the height, hypotenuse is 5, so that is 25 I had taken here. So therefore now I can write h square is equals to 25 minus b square. Now height, it is depending on base, okay, so we have h is equals to square root of 25 minus b square. Is it clear? So this is how I'm going to write, okay. So now here we are asked to find out, okay, now we had expressed h in terms of b, okay, which is that is the h is the dependent variable and b is the independent variable. So like we expressed y in terms of x, so here I had expressed h in terms of b. So first you have to form the relationship between the two variables if it is not given, okay. Like if you have in the previous 2 examples, area we already know, surface area we already know, volume we already know, so we don't have to create anything. But in this example there is no relationship between the variables, okay, so we have to form it. Actually there is the relationship, but it is not given, so we have to form the relationship between the 2 variables, okay. So we had now expressed h in terms of b, okay. Now here we have to find out dh by dt, is it? So we have to find the rate of change of height of the wall with respect to time, okay. So we have to find out that. So this is equals to, okay, so now we have this dh by, so first of all this h is depending on b, okay, so that is db, right, into, then base is depending on time, so therefore we have db by dt. So again you have to apply chain rule over here, okay. So now this is equals to, so first let me differentiate this, okay, dh by db. So first of all it's a square root function, so that will be 1 upon 2 root x, so that is 25 minus b square into, then I need to differentiate this term inside the square root. So 25 is constant, it is 0, derivative is 0. So negative b square, it is negative 2b, right? Okay, into db by dt is given as 2. So like this you will take first of all. So this is equals to 2, you can cancel it out. So I am left with here dh by dt, okay, is equals to negative 2b whole divided by square root of 25 minus b square. Is that clear, right? Okay, so now we have to find out, this is the rate of change of height with respect to time. Okay, now one thing, whenever you find the rate of change of any quantity, okay, if you are getting it in negative term like this, here we got it in terms of negative, we had not changed anything, but when you differentiate it, automatically you get a negative term over here, which means when you get a negative term, it means that quantity is decreasing. Is that clear? So height is decreasing. Okay, if you get a positive term, okay, so then it means that quantity is increasing. Height, if it is height is increasing, right? So whenever you get a rate of change in terms of negative term you get, so then it means that quantity is decreasing, right? If you get a positive term for the rate of change of any quantity, then it means that quantity is increasing. Okay, so here height is decreasing. You don't have to do anything, but since you get a negative term over here, it means the height is decreasing, right? Okay, so now we will write here. Okay, I'll write it here. So dh by dt. Now we are asked to find out when it is 4 meter away. So that is b is equals to 4. So that is equals to negative 2 into 4, okay, whole divided by square root of 25 minus b square. So that is 4 square is 16. Okay, so this is equals to negative 8 whole divided by square root of 25 minus 16 is 9. Okay, so that is 3. So we have dh by dt, okay, at the when it is basis when the distance between the bottom of the ladder and the wall is 4 meter. So this is equals to negative 8 by 3, right? So this is it. Is that clear, right? So this is the rate of change of this height is the rate of change of height, or this is the rate of change of the decreasing in height of the wall when the distance between the bottom of the ladder and the ground. Okay, so this is 4 meter. So this is how you're going to find out. Is that clear? So all the concepts are same. So you should know what do we mean by dy by dx. Okay, so that is the rate of change of y with respect to x. Okay, if it is dy by dt, then what is it? That is the rate of change of y with respect to time. So always you have this first rate of this y will depend on x is depending on t. So therefore dy by dt is equals to dy by dx into dx by dt. So the concept of chain rule is to be used when you are given a third variable time, okay, in the question. Okay, so I think now with these 3 examples you will be a little bit clear about how this derivative is to be applied in this particular topic. Okay, so you should know all the mensurations formula of class 10, because all these formulas are to be used here. So for practice today you will do exercise 5.2. So not 5, sorry, exercise 6.1. Okay, so in this exercise you will find so many questions. Okay, there are I think 19 or 20 questions in this exercise, so the number of questions is quite large. So if possible, try to do all the questions. If not, then you at least try to solve 10 questions of this exercise. Randomly you will choose, but please, when you choose the question, you try to take different types of question. Okay, so you don't take all the questions which are on the volume of cube. Okay, so all these questions will be same, so there is nothing new in that. So try to see the variations in the question and try to attempt all types of questions from this exercise. Okay, so at least you will do 10 questions from this exercise, okay, for practice. Okay, so today we had discussed the first application of derivative in the field of finding the rate of change of quantities. Okay, quantities means finding the rate of change of the quantities in mensurations. Okay, so I think this topic is quite simple because there is nothing much new. Okay, so all the ways you are using in differentiation in chain rule, these are to be applied here. Plus you should know all the formulas of mensuration of class 10, right? So in the next class we shall see the second application of derivative. So till then you will complete this exercise. If not all questions, then at least you will do 10 questions. Okay, so with 10 questions, I think you will cover all the different types of questions you have given in this exercise. Okay, so with this today I'll stop here and I'll see you in the next class. Till then, take care and stay safe. Thank you.